Hey guys, Mr. B here, and in this video we're going to be going through Chapter 12, Section 2 on chemical calculations. So I'm going to tell you right now this video is going to be a bit longer than most of the other ones, primarily because there are 5 practice problems, and there's a lot of math that's involved in these problems, so I'm going to try to take my time to explain how I'm doing each step. That way you're not confused. I know it'll be a longer video, but please, I would highly encourage you to watch the whole thing and actually watch how I solve these problems. That way you're not confused later on when you have to do some practice on your own, and especially, of course, when we have to test you on this material. So, all right, so let's jump into this here. So we're going to be learning how we use chemical equations to calculate amounts of material in moles, as well as in grams or liters or molecules, or all the different units so far that we've learned. Okay. So first thing is, in chemical calculations, mole ratios are going to be used to convert between moles of reactant and moles of product, or between moles of reactants or between moles of products. So what exactly are they talking about when we're talking about mole ratios here? Okay, so we learned in Chapter 11 how to balance chemical equations, and I'm just going to write out an equation here that you probably are all familiar with. We're going to use this as an example, okay? Okay, so this is the reaction of water. Hydrogen reacts with oxygen to make water. I've balanced it already for you. And the mole ratios that they're talking about here are the coefficients. Okay, so this big number 2 that I've written in front to balance with, and this big number 2 I've written in front to balance with, and technically in front of the oxygen there's a 1. Those are known as mole ratios. Okay, what that's basically saying is that if you start with 2 moles of hydrogen, you will need to react it with 1 mole of oxygen, and you will produce 2 moles of H2O. Okay, that's what that is saying. So these coefficients that we've used to balance the equation with are mole ratios. And what this is basically saying is we can use these to convert between moles of different things in the reaction. So let's say, for example, that I wanted to know, let's say that I'm starting with 4 moles of H2, okay, instead of 2, starting with 4. How many moles of oxygen am I going to need to react with 4 moles of H2? Well, based on this equation, or this reaction here, it's a 2-to-1 ratio. So between the hydrogen and the oxygen, every 2 moles of hydrogen that I use, I only need to use 1 mole of oxygen, right? Or basically half. So if I start with 4 moles of hydrogen, how many moles of oxygen am I going to need? I'm only going to need half, right? So I'll need 2 moles of oxygen. Also, in the reaction, for every 2 moles of hydrogen that I begin with, I will make 2 moles of water. Basically, this is a 1-to-1 ratio. So the exact same amount of moles of hydrogen that I begin with, I will get the exact same amount of moles of water in the end. So if I start with 4 moles of hydrogen, I'm then going to get out 4 moles of water, okay? Because it's a 1-to-1 ratio between these two things. So these numbers, these coefficients that we use to balance, can basically be used to convert between anything in a reaction. Okay, they're very important, but the key thing to know is they only can be used if you are in the units of moles. If you're not in the units of moles, let's say you're in grams or liters or something else, you cannot use these numbers to convert. Okay, so it's very important that we get into the unit of moles first, so that way we can use these to convert between stuff. Okay. So a mole ratio is a conversion factor. It's derived from the coefficients of a balanced chemical equation interpreted in terms of moles. I just showed you this in the previous little part. They have this little equation here, but for the most part, we're just going to ignore that because I think it's just more confusing than anything. So, all right, so to determine the number of moles in a sample of a compound, most of the time, first we have to measure the mass of the sample. Then we have to use the molar mass to calculate the number of moles in that mass. Okay, now this, again, is basically saying that in the laboratory, we oftentimes don't measure moles of material. We don't have any equipment or any kind of tools that will measure moles. We have scales or balances, and those measure mass, right? They measure grams. So if we want to first find the number of moles that we have in a sample, we'll have to take the mass of the sample and convert that into moles using the molar mass of the material. Then from there, we can use molar ratios to then convert between different amounts of stuff, okay? So we're basically taking like a lot of stuff from chapter 10, which is the whole conversions, grams, moles thing, and we're now using it here in chapter 12, okay? All right, so let's take a look at an example problem. So it says, how many moles of ammonia are produced when 0.60 moles of nitrogen reacts with hydrogen? All right, so first off, the one part about this problem that's kind of difficult is that they're not telling you the chemical formula for ammonia. They're just kind of assuming you know what it is. So first thing is we need to write out the chemical reaction, okay? Pretty much if you don't have a balanced chemical reaction, you can't do anything, okay? So you need to have a balanced chemical reaction no matter what you're dealing with. Now, ammonia is NH3. Excuse me. So we're going to have H2, okay, which is hydrogen gas, reacting with N2, which is nitrogen gas, and we're going to make ammonia, okay, which is NH3. Now, I would usually give you the chemical formula for ammonia, okay? But for nitrogen reacting with hydrogen, right, you guys can write this, no problem. The ammonia is NH3. We also have to balance this reaction. So real quickly to balance this, we're going to need to make changes like this. All right, so here's our balanced reaction. And now the question is asking, if we are starting with 0.60 moles of N2, okay, because it says how many moles of ammonia are produced when 0.60 moles of nitrogen reacts with hydrogen. So basically we're starting with 0.60 moles of N2, and we're going to get an answer in some number of moles of NH3, okay, ammonia. And to do this, it's just going to be a conversion problem. Now the conversion factor is given to us in the reaction. Okay, so every 1, there's a 1 there, even though it's not written, there's a 1, okay? So for every 1 mole of N2 that we start with, we are going to end up making 2 moles of NH3, okay? It's a 1 to 2 ratio. It's a 1 to 2 ratio. So seeing as we're starting with moles of N2 here, if we use dimensional analysis, we can convert moles of N2 into moles of NH3, which is what the problem's asking for. How many moles of ammonia are produced? So since we're starting with moles of N2, we want to have the 2 moles of NH3 on the top of our fraction. And we want to have the 1 mole of N2 on the bottom of our fraction. Okay, like this. So moles of N2 will cancel with moles of N2 in the conversion factor. And we're basically going to take 0.60 and multiply that by 2. And when we're done, we're going to have an answer that is in the units of moles of NH3. So do this on a calculator real quick. And I get 1.2 moles of NH3 will be produced. Okay, and that's it. So it's basically just a conversion problem like we dealt with in previous chapters. But now we're going to be using these coefficients as conversion factors between moles in the reaction. All right, taking a look then at the next part. So there are some steps here to help you. Okay, now that last problem we just did was only going from moles of one material to moles of another material. However, a lot of times you are going to be starting in a unit that is not moles. Okay, it could be like mass, grams, or it could be liters, or it could be molecules or some type of particle. So understand that there are some steps here that can kind of help you. But step 1 is always going to be to change the units of whatever you're starting with into moles. Okay, now this is specifically talking about if you're starting with grams. So you're going to change the mass of G. Okay, G is just whatever the material you're starting with. So you're going to change the mass of the material you're starting with to moles of that material by using molar mass. If instead we had a number of liters instead of mass, this would say change the liters of G to moles of G by using molar volume. okay, which is the conversion factor between moles and liters. Or let's say we are given molecules or some type of particle like atoms. This would say change the atoms of G to moles of G by using Avogadro's number. Okay, that's that conversion factor. Either way, though, step one is always going to be change the units of whatever the material you're starting with into moles of that material by using whatever conversion factor you need to get into moles. Step two, you're then going to change the moles of the starting material to moles of whatever the material is that the problem wants you to find by using the mole ratios from the balanced equation. So you're going to use the coefficients in the balanced equation to convert from 1 mole of one material to another mole of another material. Okay, it might be a 1-to-1 ratio, could be 1-to-2, could be 2-to-3, either way. And then lastly, you'll then convert your moles of that material that you just calculated into whatever unit the problem wants you to end in. So if they want to find a mass, you'll need to take the moles of that material and convert it back into grams by using molar mass. If they want you to find liters of that material, you'll need to take your moles and convert that into liters using molar volume. Okay? Or if they want you to find some type of particle like molecules or atoms, you'll need to take your moles and convert it into molecules or atoms by using Avogadro's number. Okay? So step one, convert into moles. Step two, convert from moles of one thing to moles of another thing using the coefficients in the reaction. Step three, convert back from moles into whatever unit that they want you to find. All right, so let's take a look at some example problems here where we'll break down this process. So this problem says, calculate the number of grams of NH3 produced by the reaction of 5.40 grams of hydrogen with an excess of nitrogen, and they're giving us the balanced equation. All right, so this is the same exact reaction as from the previous problem, though they're giving it to us here rather than we having to write it out ourselves. So the problem is basically asking us, if we have 5.40 grams of hydrogen, okay, H2, they want us to calculate the number of grams of NH3. Excuse me again, sorry. So we're going to start with 5.40 grams of H2, okay, hydrogen. It's reacting with an excess of nitrogen. Pretty much it's just telling you there's a lot of nitrogen there, okay? That part doesn't matter. And they want us to calculate the number of grams of NH3. All right. So the steps that we have is step one, convert grams of H2 into moles of H2. Okay, that's step one. Step two, convert moles of H2 into moles of NH3. And step three is convert moles of NH3 into grams of NH3. Okay, because the problem is asking us to calculate number of grams. All right, so let's do each part of this problem. Okay, and we'll do it in black so it'll stand out more. All right, so we're starting with 5.40 grams of H2. First step, we have to convert that into moles of H2. All right, so to get this into moles of H2, we'll need to know the molar mass of H2, right? So we can look on a periodic table. I don't have mine in front of me. I hope you do. But if not, actually I lied. I do have mine here. Sorry. So molar mass of H2 can be found right here. It is basically 1 gram per mole. So if there's 2 H's, H2 is going to have a molar mass of 2 grams per mole. So we're going to set this up to have 1 mole of H2 on the top divided by 2 grams of H2 on the bottom. Okay. We're going to do this because we want grams of H2 to cancel with grams of H2, right? We want to get into moles of H2. All right, so if we do this on a calculator, 5.40 times 1 divided by 2, I get 2.7 moles of H2 in the first part. Okay, next part now is convert moles of H2 into moles of NH3. So we have 2.7 moles of H2. I'll change the color here to black again. 2.7 moles of H2. We need to convert this into moles of NH3. Now in the reaction, it's a 3-to-2 ratio. So basically it's just saying that for every 2 moles of NH3 that we make, we need to start with 3 moles of H2. Okay? Now you can see that I'm setting this up just like I did in the step 1 with my conversion factor now being the coefficients from the reaction right here. And I'm also making sure that I set up my units properly so that I cancel out moles of H2 and I'm left in moles of NH3. Okay, so we're still using our dimensional analysis skills. So we're going to take 2.7 times 2 divide by 3. And we will get 1.8 moles of NH3 now. Okay, so we have 1.8 moles of NH3 after that step. Okay, now the last step is we are now going to convert those moles of NH3 into grams of NH3 because they do want us to find the number of grams, not moles. Okay, so basically we're doing step 1, but we're just going backwards. So 1.8 moles of NH3. In order to convert this into grams of NH3, we need to know the molar mass of NH3. Okay, so again, if you look on a periodic table, nitrogen over here has a molar mass of about 14. H has a molar mass of 1, and there are 3 of them. So the molar mass for NH3 is basically about 17 grams per mole. So 17 grams of NH3 over 1 mole of NH3. Okay, like so. Again, I'm going to cancel out my moles of NH3 and get into grams of NH3. And then that would be my final answer because that's what the problem is asking for. So take 1.8 times that by 17 and I get 30.6 grams of NH3 would be produced. Okay. So again, calculate the number of grams of NH3 produced by 5.40 grams of hydrogen reacting with nitrogen. So we started with 5.40 grams of hydrogen, converted into moles, okay, using molar mass. That's what step 1 is. Then we took that moles and we converted that into moles of NH3 using the coefficients from the reaction. Okay, it's a 2 to 3 ratio to get moles of NH3. Then lastly, we took those moles of NH3 and converted them back into grams of NH3 because that is what the problem asked for by using molar mass of NH3. There's our final part, okay? All right, so hopefully that makes sense. We are going to do, though, a few more problems. And again, this video will be a little bit longer because of that. But either way, I want to make sure we take our time and understand what's going on. Now, I mentioned before, what about other stoichiometric calculations? Or basically, what about other units, right? Let's say that we're not calculating mass, but instead we want liters or molecules or atoms, right? Or some other unit. In a typical stoichiometric problem, the given quantity is first going to be converted to moles. Okay, so no matter what problem you are given, step 1 is always convert into moles using whatever conversion factor you need to use, whether it be molar mass, molar volume, Avogadro's number. Then we'll use the mole ratios from the balanced equation to calculate the number of moles of the material we're starting with to get into the moles of material that we want. And then lastly, the moles then of that are converted back to whatever other unit the problem wants using whatever conversion factor we need. So if they want to give, if our final answer needs to be in grams, we'll then need to take those moles, convert to grams using molar mass, like we just did in the previous problem. If they want liters, we'll need to take those moles and convert into liters using molar volume, right? Or if they want particles like molecules, we'll need to convert using Avogadro's number. So there's a nice little flow chart here that kind of shows this. If we are given mass of a material, we'll convert from mass to moles, okay, using molar mass. Then we'll convert from moles of one material to moles of another material using the ratios from the equation. And then lastly, we'll convert moles of that material back into grams using molar mass. But again, we can basically use this little flow chart with any unit we're beginning with. So if we're starting with some type of particle, we use Avogadro's number to convert to moles. If we're starting with liters or volume, we'll use molar volume to convert into moles. Okay, and the middle one here shows the mass, which you've already done. Then in the middle, it's always the same step. Moles of one material to moles of another using mole ratios from the reaction. And then lastly, convert those moles back into whatever unit the problem wants you to using the appropriate conversion factor. Okay? All right, so let's take a look at another problem where we're going to do this. So this problem says, how many molecules of oxygen are produced when 29.2 grams of water is decomposed by electrolysis according to this balanced equation? Okay, so in this problem, we are starting with, they're asking how many molecules of oxygen are produced when 29.2 grams of water, okay, H2O, is decomposed by electrolysis, blah, 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 blah. Okay, so we have 29.2 grams of H2O, and they want us to get a final answer in molecules of O2, right, oxygen. Okay, So again, we'll set up the same steps. So step 1, convert grams of H2O into moles of H2O. Okay, step 1 is always convert into moles. If you're not in moles already, convert into moles. Step 2, convert moles of H2O into moles of O2. Okay, because you need to get into oxygen units of some kind eventually. And then step 3, we are then going to convert moles of O2, and now we're going to convert these into molecules of O2, because the problem wants us to get an answer in molecules of oxygen, not moles. Okay, so let's do each of these steps. We'll do it in black so it stands out. Okay, so step 1, convert grams of H2O into moles of H2O. So we have 29.2 grams of H2O. To convert this into moles, we are going to need to know the molar mass of H2O. Okay, so on your periodic table, find hydrogen. 2 hydrogens plus 1 oxygen. Okay, hydrogen is basically 1. There's 2 of them, so that's 2. Oxygen is 16, so 2 plus 16 is 18 grams per mole. And again, we'll set up our fraction properly. So 1 mole of H2O on the top over 18 grams of H2O on the bottom. So that way our grams of H2O cancel out with each other. Okay, so grams of H2O will cancel with grams of H2O. So we're basically going to take 29.2 and divide that by 18. So I get, for this first step, 1.62 moles of H2O. Then from here, in our second part, we're going to take our 1.62 moles of H2O, and we're going to convert those from moles of H2O to moles of oxygen. Okay, now in the reaction, it's a 2-to-1 ratio. Okay, we'll make 2 moles of water is needed to begin with, but for every 2 moles of water, we're only going to make 1 mole of oxygen. So we're going to, again, go from moles of H2O to moles of O2, and the conversion factor is a 2-to-1 ratio. So for every 1 mole of O2 that we make, we will have 2 moles of H2O that we start with. Okay, again, you can see that I'm setting up my fractions so that my moles of H2O, which I'm beginning with, are on the bottom of my conversion factor. Okay, again, I'm getting these numbers, 1 mole of O2 for every 2 moles of H2O right here from the reaction. 2 moles of H2O, 1 O2. Okay, there's no number written, that's a 1. Okay, so we'll take 1.62 and basically divide that by 2. So we are going to get 0.81 moles of oxygen after that step. So now the last part here is we are going to take those moles of oxygen, so 0.81 moles of oxygen, and convert that into molecules of oxygen. Okay, and now to do that, of course, to go from moles to a particle, we need to use Avogadro's number, which is 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd molecules of O2 over 1 mole of O2. Okay, and I know I'm kind of running out of space here, but either way, in case we have moles of O2 to begin with, that will cancel out with moles of O2 down here on our conversion factor. And we're basically going to take 0.81 times 6.02 times 10 to the 23rd. And our final answer is going to be 4.88 times 10 to the 23rd molecules of oxygen. Oh, I did not mean to do that. My bad. There we go. Okay, right? And there we go. That is our final answer, because that's what they want us to find. How many molecules of oxygen are produced? All right, so hopefully that kind of, again, gives you the steps you need to do these kinds of problems. They look really confusing, but it's the same steps every time, okay? Step 1, convert to moles. Step 2, go from moles of one thing to moles of another thing. Step 3, convert from moles to whatever unit they want you to end in, if they don't want you to end in moles. Okay, if they do want you to end in moles, then once you get to step 3, you're pretty much done. So, all right, let's take a look at another one. So this one says nitrogen monoxide and oxygen gas combine to form the brown gas nitrogen dioxide, which contributes to photochemical smog. How many liters of nitrogen dioxide are produced when 34 liters of oxygen react with an excess of nitrogen monoxide? Assume conditions of STP. Okay, so we have 34 liters of oxygen, okay, O2. So the question is how many liters, of nitrogen dioxide, which is the NO2 in this problem, how many liters of nitrogen dioxide are produced when 34 liters of oxygen react with nitrogen monoxide? So we're basically going to go from liters of O2 to liters of NO2. And I apologize, I'm sick here, so I got a lot of boogers. I apologize again. So we're going to convert liters of O2 into moles of O2. Step 1, okay, always step 1 is convert into moles. Okay, always convert into moles. Step 2, convert moles of O2 into moles of NO2. And then step 3 is convert moles of NO2. And in this problem, they want us to get their final answer in liters. This is how many liters. We're going to convert moles of NO2 into liters of NO2. Okay? All right. So let's get going on this. Put this in black. So we're going to start with 34 liters of O2. And we are going to get this into moles of O2. Now, since this is in liters, the conversion factor to go from liters to moles is molar volume. Okay, now that is 22.4 liters per mole. You may or may not remember that number because, again, it was from like chapter 10 and we're now in chapter 12. So if we set up our fraction, 1 mole of O2 on the top over 22.4 liters of O2 on the bottom. Okay, that is our conversion factor. So liters of O2 will cancel with liters of O2 that we're beginning with. So we're going to take 34 and divide that by 22.4. So 34 divided by 22.4. And I'm just going to round this to 3 sig figs. So 1.52 moles of O2. All right, so there's that first part. And then we're going to take our 1.52 moles of oxygen, and we're going to convert this into moles of NO2. To do that, we need to know the mole ratio between the two. So looking in the reaction, for every 1 mole of oxygen, we're making 2 moles of NO2. So it's a 1 to 2 ratio. Okay, so again, we'll set up our fractions. So for every 2 moles of NO2 that we make, we are going to start with 1 mole of O2. Okay, again, those numbers are coming directly from the balanced equation written up above. So moles of O2 will cancel out with moles of O2. We're going to take 1.52, multiply that basically by 2, and I get 3.04 moles of NO2. Okay, and then the last part is we are going to convert our moles of NO2, so 3.04 moles of NO2, and we're going to convert that into liters because the question is asking how many liters of nitrogen dioxide are produced. Okay, so it's going to end up in liters of NO2. And to do that, we'll use molar volume again, which we did in step 1. So it's going to be basically the same exact conversion, only we're going to flip the fraction. Okay, so the 22.4 liters of NO2 will be on the top, and the 1 mole of NO2 will be on the bottom. That way, again, our moles of NO2 cancel out. Okay, again, dimensional analysis is important. And basically, we're going to take 3.04 times 22.4. And again, rounding to 3 significant figures, I get 68.1 liters of NO2. Why stop doing this? I don't know why it likes to do that. Okay. We got 68.1 liters of NO2 is how many liters of nitrogen dioxide we can produce from 34 liters of oxygen gas. Okay. All right. I believe there's one more. And then hopefully you understand because that's the last one in here, okay? So you got one more to do. Here we go. Last one. Assuming STP, how many milliliters of oxygen are needed to produce 20.4 milliliters of SO3 according to this balanced equation? All right, now this one is interesting. And the reason why it's interesting is because they're starting off in the unit of milliliters rather than liters. And they also want us to get a final answer in milliliters, not liters. Okay. Now, this really isn't any different than any of the other ones we've done. Okay. Step 1 is still going to be convert ml of milliliters of SO3 into moles of SO3. Okay, that's step 1, just like in the last ones. Step 2 is going to be going to convert moles of SO3 into moles of O2. And lastly, we're going to convert moles of O2 into, I guess, all right, this is not going to make sense for a second, but we're going to explain, into milliliters. Okay, now this is what we have written down. Okay, we're going to convert milliliters of SO3 into moles of SO3, convert moles of SO3 into moles of O2, then convert moles of O2 into milliliters of O2. Now, the problem with this, however, is the conversion factor that we have that deals with anything with volume is molar volume, and that deals with liters and moles, okay, not milliliters. So even though step 1, I said convert milliliters of SO3 into moles of SO3, that's technically not step 1. Step 1 is convert milliliters of SO3 into liters of SO3. Okay, that's step 1. Once we've got liters of SO3, then we can convert liters of SO3 into moles of SO3. Once we've got moles of SO3, we can convert moles of SO3 into moles of O2. Once we have moles of O2, we can convert those moles of O2 into liters of O2, because that's our conversion factor, deals with liters. And then lastly, we will convert our liters of O2 into milliliters of O2, because the final answer does want milliliters. Okay, so it's kind of like we're adding one additional step on at the beginning and the end, and that is just having to get from milliliters into liters. That way we can use our molar volume conversion. Okay, now this is just a metric conversion. So basically 20.4 milliliters of SO3. Milli means 1,000 times smaller. So there are 1,000 milliliters in 1 liter. Okay, so to do this conversion, we're basically going to multiply this by 1 liter of SO3 over 1,000 milliliters of SO3. And just using dimensional analysis, we can see that if we're starting with milliliters of SO3, then we need to put the 1,000 milliliters of SO3 on the bottom so that it cancels and we get into liters of SO3. Okay, so we're basically just going to take 20.4 and divide that by 1,000 to get this into liters. So I get 0.0204 liters. All right, now once I've got into liters, then from this point, it's pretty much doing the exact same stuff we did on all the other problems we just did. So liters of SO3, we're going to get this into moles of SO3. To go from liters to moles, we need to use molar volume. Seeing as we're starting with liters of SO3, we want to have 1 mole of SO3 on the top, 22.4 liters of SO3 on the bottom. Okay, that way again, moles of SO3 cancel, or I'm sorry, liters of SO3 cancel out with each other. So we'll cancel those. That will get us into moles. So basically we're going to take 0.0204 and divide that by 22.4. We're getting really small numbers here. So 0.00091. I guess I'm around to 3 sig figs. 1. Okay, if we round to 3 significant figures. All right, so now we have moles of SO3. So let's just copy and paste this. Okay, so there's moles of SO3. And now we are going to get into moles of O2. To get into moles, from moles of one material to moles of another, we need to use the conversion factors in the equation. It's a 2-to-1 ratio. So for every 2 moles of SO3 that we make, we only need 1 mole of O2. So since we're starting with moles of SO3, we're going to have the 1 mole of O2 on the top, the 2 moles of SO3 on the bottom, okay, like this. So take our answer from previous, and we're going to basically just divide that by 2. So now we get 0.000455 moles of O2. Okay, we're going to take now finally those moles of O2 and convert them into liters of O2, which isn't our final answer because we need to get that into milliliters, but we'll use our molar volume to do that. So it's the same conversion that we did right here in step 2. Okay, we just got to flip the conversion. So we're going to have the 22.4 liters of O2 on the top and the 1 mole of O2 on the bottom. Okay, again, that way moles of O2 cancel out with each other. And we're going to have liters of O2. So we'll take our answer from before and just times up by 22.4. I get 0.0102. And then finally, we need to convert that into milliliters. Okay, because they do want how many milliliters of oxygen. So the last thing now is like doing step 1. We're going to convert back into milliliters by using the conversion factor of 1,000 milliliters per 1 liter. Okay, so we're going to get into milliliters of O2. So since we're starting with liters of O2, 1,000 milliliters of O2 will be on the top. 1 liter of O2 will be on the bottom. So that way, liters of O2 cancel out with each other. And we are finally going to be in milliliters of O2, which is what our answer needs to be in. So take our previous one, 0.012, times that by 1,000. And we get, as a final answer, 10... Hitting buttons here, my bad. 10.2 milliliters of oxygen. Okay? Now, that is probably the longest problem that you would ever face, okay, in this chapter for the most part. A lot of conversions, but we've learned how to do conversions, okay? We've learned how to convert between liters and moles. We've learned how to convert between grams and moles. We've learned how to convert between milliliters and liters, okay? This is just a metric conversion. So all these conversions that we're doing, although it looks complicated, we know how to do all this, okay? It's just trying to figure out the process to make sure we know what unit we need to get into next and what conversion factor we need to get there, okay? All right, so there are some practice problems, of course, at the end of this quizzes. I will have a video actually of me going over those quizzes problems in quizzes rather than doing them in the slides like I usually do, because the ones in the slides here are a little bit different. So if you're confused, of course, need help as you're going through those practice problems, go take a look at that video and I will show you how to go through every single one of them. But use this little step-by-step little guide here to help you, okay? If you need to go back into chapter 10 to look at the conversion factors, do so, okay? Chapter 10.2, at the end of it has the mole roadmap. If you go into the teacher slides for 10.2, you'll find the mole roadmap, which has all the little steps and conversion factors and stuff. So anyway, that is it for this video. Thank you for watching. Hopefully that helped you. And again, as always, if you have any questions or you want to go over stuff, feel free to email me, reach out so we can do so. All right, guys, I'm Mr. B. Thanks for watching. I'll see you in the next one. Bye.